So in the beginning, I would just like to introduce the group that I am a part of. It is the group based in Vienna, and it is a group of nanomagnetism and magnonics, and it has a subgroup. It is the super spin lab, and that means we have this unique thing where we can connect lots of magnetism and magnonics together with superconductivity, and this leads to a lot of research topics that are shown here, some of them. And the contributors to this work is also Stephanie North and my supervisor, Alexander Dobrovolsky. So going to the outline, I will be speaking about these nanostructured samples that have these kinds of grooves, and I will explain how we can achieve in these grooves the vortex guiding effect and ratchet effect. And then in the second part, I will talk how we use these two effects to influence the vortex dynamics as well as the AC and DC interference or Shapiro steps. So in type 2 superconductors, we know we have vortices, and they like to organize each other in these abricus of lattices that are very nice and symmetrical. And when we pass a current through this kind of sample, we know there is a Lorentzian type of force, the Magnus force, that starts to move our vortices. And we have a very nice and simple way to make observations about the dynamics of vortices, and that's by doing these current voltage curves. So just a simple 4-point method, and we can talk about how they are moving. So where we have the plateau, it means that they are all pinned. Once they start moving, there will be dissipation of energy, voltage is raising, and it all comes to a point, the flux flow instability, where it comes to a very quick abrupt jump from superconducting to the normal conducting state. And in our structures, we would like to influence the dynamics. And the two effects, as I said, that we want to use is the guiding effect. Guiding effect, a very simple real-life example is we want to go directly to the counter. We can't. We have to follow the railing. And that's exactly what happens in our nanostructured grooves. So the direction of our motion will be deflected from the one that is given to the vortices from the driving force. And the second effect, there was a lot of talking about ratchet effect in the first talk, so just to simply repeat, it's like this example in the animation, the forward direction is going to be different, or in this case, the other direction is not allowed at all. So that's the ratchet effect. And the motivation is that we would also like to influence the Shapiro steps. Many of you know the Shapiro steps from your school books, that you learned that Shapiro steps come into play in Josephson junction systems. So we know there is a weak link. Oops. So if there is a weak link, and we now we irradiate it with an electromagnetic wave, in the current voltage curve, we see the appearance of Shapiro steps exactly at these voltage steps. The Josephson junction system can be described by the resistively shunted model. And in this model, we get to the equation of a damped pendulum. And the damped pendulum equation is equal to the equation of a mass moving through a system of in a washboard system. So basically, a mass hopping in between these grooves. And that gives us an idea that we should observe these kind of Shapiro steps in all systems that have some kind of inner symmetry, and we irradiate them with and we add some AC pulses, AC current. So that was first already observed for abricus of vortices, because as I showed in the beginning, the picture of the abricus of vortices, they themselves are very symmetrically ordered. So when we add AC current, we will see Shapiro steps. But these are not that very well observable. So what was done next is these nanoengineering systems with the grooves. So the symmetry is now higher. And in this system, we really see very, very nice Shapiro steps now with this equation. Another thing, because we are influencing the vortex dynamics, we can achieve very high vortex velocities. The reasoning why ordered vortices cause high vortex velocities, I can explain later if someone is interested. But the question maybe that many of you have is, why would I even want it? For instance, the chair had a very nice talk previously. How can we improve pinning to pin my vortices? So why would I want to have high vortex velocities? And the answer is that when we put the superconductor in touch with a ferromagnet, at very high vortex velocities, it comes to a Cherenkov-like generation of spin waves in the ferromagnet. And what is interesting now for us is, again, looking at the current voltage curves. And even here, we see this plateau, or this step. And this exactly happens when it comes to the generation of the spin wave. And what are we going to be also looking in our systems is at the angle dependence. And the reason is that we don't really know under which angle our spin wave is being generated. So by observing this in a system that we can easily simulate, we could then make conclusions to this system and figure out the direction of the spin waves. And another one is the ratchet effect that is used for Fluxon pumps and lenses. And recently in this paper, it was also used, again, superconductor in touch with ferromagnet, for the modulation of the spin wave transmission. So I already explained the guiding effect is achieved by these grooves that can either be made by thickness modulation or by making superconducting stripe on top of a ferromagnet or vice versa. But if we want the ratchet effect, what we need to introduce is some kind of asymmetry. So the asymmetry, we have a fixed internal asymmetry, and this means that the structure itself will contain the asymmetry. So we can see here we have a hard slope and we have an easy slope, and that translates to the pinning potential. So when we look at the pinning potential, there will be a direction in the direction of the hard slope that will be a hard direction, and in the easy slope, the easy direction. Next, what happens when we introduce a DC current? So when we introduce a DC current and now we look at the effective pinning potential, what happens is it's the effective pinning potential will cause through this DC current this tilting. On the right-hand side, we see what happens when the current flowing to the right. On the left-hand side, when it flows to the left. So we already have our system. It is a system of these grooves with an internal asymmetry, and now we introduce our AC current. And as in the beginning I said, this leads to the appearance of these Shapiro steps. Here just a simple explanation why. Every step will appear exactly when one or a multiple of these hopping periods during one AC cycle will be equal to the period of my structure. And then here is just the explanation about how do we characterize the angle that we are looking at. So the angle is going to be the angle of the current towards the grooves of the structure. That means when the angle is equal to 0, current is parallel to my grooves, and vortices try to move across these lines, and when it's 90, they flow along them. In the simulations, to describe the physics behind this, is used a very simple equation, the Langevin equation. But with this simple equation, we can very nicely describe all the effects that we have, ratchet and guiding effect. What are the contributions? We have the vortex viscosity. Next, we have the Hall term that in our system is very small and we can omit it. Then we have the Lorentzian type force or Magnus force, where we introduce exactly our current together with the angle that I showed. Next, it's the pinning force that is dependent of the pinning potential of the structure. Then there is a thermal term, which is equal to the Gaussian white noise. And so last is the vortex force. We know when we have two vortices, these repel each other. But in the special case, we'll be looking at matching fields. That means that we will have exactly one row of vortices in each of the grooves. And this is when these equal each other out. And so we can also omit this term. So all the term we stay with is vortex viscosity, pinning force, and Magnus force. This is a picture of the experimental setup. Here is our sample. It's actually ferromagnetic stripes on top of a superconductor. So when we look at the pinning potential, we see that the lowest dip is on the top of the hill. This is Oxford cryostat that was measured in. Then we have the sample holder, cryogenic sample holder, and then the measurement setup. So AC current from VNA, DC current source, and we measure the voltage. And here are the experimental results. And now in the next slides, I will show the comparison with the Langevin equation simulations, and I will show that really we can with the help of this Langevin equation explain and correctly reproduce what we saw in experiment. So first we will look at the pinning potential asymmetry and how it influences the Shapiro steps. So in experiment we made these grooves, and when we want to when we want to look at the simulations, we introduce these grooves as the pinning potential by this equation, with E as the asymmetry parameter. This basically means when E is 0, almost 0, we have very nice symmetrical grooves. When E is non-equal to 0, we really have this easy slope and hard slope. And now how does that translate into the experiment? We see that for E is equal to 0, that the Shapiro steps will be symmetrical towards the 0 of the DC current, but with hiring of the asymmetry parameter, we will see that the depinning current will be moved to higher currents in the direction of the hard slope, but to lower currents in the direction of the easy slope. Next is the AC frequency. So with AC frequency, when the AC frequency is equal to 0, there will be no Shapiro steps because we have nothing to synchronate with. And then the larger is the frequency, because of the equation that I showed in the beginning, the first step will always appear at higher and higher voltages, and at very high frequencies we don't even see any step because it comes to the flux flow instability sooner than we could see the first step. Here is how it behaves with temperature. It's actually the inverse temperature. So at the lowest temperatures we see very nice Shapiro steps, and at high temperatures it's smearing out of the steps because we add energy to the system, and so the effective pinning potential is actually lowered and it's easier for them to move. No? Okay. Now the ratchet effect, where can we best observe it is when we look at the plots the voltages plotted against AC current. And very interesting how what we can see is the solid lines are positive DC currents. And what we can see that even at positive DC currents we have negative voltages here. And that is exactly the consequence of this hard slope and this easy slope. So there will be a point, exactly the point once it starts going to the negative, where the vortex is already able to move in the direction opposite to the DC current, and only from the point when it switches back, it's got enough amplitude of the current to move again in the direction of the DC current, so also to go through the hard slope direction. And this is in the low frequency regime, but when we go to the high frequency regime, we don't observe this at all. And the reason is that now the frequency is so large that our vortex is actually only moving in one of the wells and doesn't have time to hop from one to the other. Now we have the angle dependence. So first let's look at the border cases. When alpha is equal to 0, my vortexes are going perpendicular to the grooves, and this leads to really nice Shapiro steps. While when alpha is equal to 90, moves along it, that means we will have a constant resistivity, and that leads to this linear appearance of the voltage to current. But what's happening in between? So what is the difference now? When we are changing the angle and we are moving between the grooves, we are changing the length of the trajectory that it needs from one of the hills to the other. So it's actually getting larger, which means we will need more time to do this, and that leads to a smaller frequency. And this is actually the pinning frequency that we put here. So the F that we will have here is actually getting larger. And this is the F that we use to calculate our position of the Shapiro steps, at what voltages they are. So this one is getting higher, so really the voltages should be getting higher. And this is what we really observe. So as the angle is getting larger, the appearance of the Shapiro steps appear at larger and larger voltages. And this coincides also with the experimental results, so very nicely we can see how we can replicate this with simulation. And this leads me to the conclusions. So one of the most important messages is really this increase of the Shapira step voltage with the angle, and also how nicely we can use the Langevin simulation to replicate all of the experimental results. Thank you for your attention.
Thank you very much, Barbara, for your interesting presentation. And my question concerns your interpretation using the Langevin equation. Langevin contains a stochastical force. And in order to make this comparison, you need to attach some meaning and some value to this force. How do you use the magnitude of this stochastical force, which gives you a possibility to explain the experimental data? Do you know this force a priori, or you make it for matching? Thank you.
Okay, let's go back to the... So all of the measurements are done at matching fields, because only then we can simplify the Langevin equations, because we can leave all of the other terms, but I'm not really sure what was the question.
In the stochastic force, you need the magnitude of this force. Do you know it from some measurements or from literature? Or you assign some value to this force?
Because all of the parameters that are done in the simulations, they are normalized, and they are. I think the force would be also normalized to the pinning force, and that's from experiment. Now I'm not sure.
While we're on this, while we're on this slide, for FTH, for the thermal energy that you mentioned as Gaussian white noise, what is this exactly? Does this consider vortex creep?
This is something. Whoops, maybe we can't have. This is something that when we look at the statistical average, it's always just equal to 0. It's just introducing the thermal noise in the system.
Okay, so it doesn't consider creep itself. It's just, okay. Thank you.